one of the most baffling dark openings and peculiar phenomena in the universe, remains the focus of intense examination and interest among space experts, physicists, and other scientists alike. Referred to for their monstrous total weight and gravitational pull, the absence of visible light from them marks a limit beyond which the established rules of physical science must stop applying. In 1916, Albert Einstein speculated, as a result of his theory of general relativity, about dark openings. These were simply speculative until mechanical advancements allowed their indirect identification in the 21st century. The 1960s marked the turning point, when experts in space research discovered, by accident, a group of stars, an unusual celestial object, a brilliant blue star producing high-energy X-rays. This star, circling an unnoticed companion, challenged regular explanations until it was revealed to be caught in a gravitational hug with a massive dark object, Cygnus X-1. The clear discovery of Cygnus X-1 confirmed the existence of dark openings as evidence and began a new phase of research. Cygnus X-1, discovered about 6,000 light-years away from Earth, boasts staggering properties. It is incredibly dense and applies a force of gravity so strong that not even light can escape its grasp. This defining feature earned it the moniker dark opening, which captures the essence of these mysterious objects. Subsequent research has shown that a smattering of dark openings exist throughout the universe. Estimates imply that the Milky Way galaxy alone may be home to over 100 million dark openings. Despite their elusive nature, which facilitates accurate detection to be challenging, space experts have identified a number of candidates from our galaxy. These range from stellar dark openings, formed from the remnants of massive stars, to extremely massive dark openings located at the centers of galaxies. Their gravitational impact goes well beyond their immediate vicinity, shaping the elements of cosmic development and influencing the fate of surrounding matter. Objects that get too close to a pitch-black opening confront a destiny set by its relentless force. They are drawn toward the event horizon, the final turning point, where they are subjected to extreme tidal forces and, in the end, consumed by the singularity at the core. This catastrophic interaction is referred to as spaghettification, an extreme manifestation of a dark opening's gravitational strength. As an object approaches the event horizon, the gravitational gradient across its length stretches it to its limits, contorting it into a filamentary structure resembling strands of spaghetti. The forces applied by the dark opening overpower the internal bonds keeping the object intact, resulting in its disintegration into a stream of matter destined to merge with the singularity. Despite the allure of dark openings as invaluable laboratories for testing the limits of physical theory, they remain shrouded in mystery and intrigue. The mission to unravel their secrets continues unabated, driven by a desire to comprehend the fundamental nature of space-time and gravity itself. In the vastness of the universe, dark openings stand as silent sentinels, beckoning humanity to explore the depths of the unknown and expand the limits of human understanding. Despite the considerable distance separating us from the closest known dark opening, roughly 1,500 light-years away, questions and concerns about their potential impact remained. In 2019, researchers achieved a historic breakthrough by capturing the first clear image of a dark opening, specifically M87, which is in the middle of the M87 galaxy. This remarkable accomplishment provided crucial insights into the nature of dark openings and their elusive structure. The visual data revealed that dark openings have intricate layers, challenging the conventional conception of them as solitary entities of pure nothingness. Through thorough investigation and image stitching, researchers identified 3 distinct layers within a dark opening. At the outermost layer lies the event horizon, a critical boundary marking the point of no return. Once an object crosses this threshold, gravitational forces become insurmountable, ensuring its inevitable plunge into the dark opening's depths. Moving inward, the photon sphere constitutes the second layer, where light orbits the dark opening in perpetual bondage. Any photons that venture into this realm succumb to the overwhelming gravitational pull, trapped forever within the cosmic embrace of the dark opening. At the heart of the dark opening lies the singularity, the third and final layer, where the physical laws reach their ultimate limits. Matter undergoes unfathomable compression, collapsing into a point of infinite density. Within this mysterious singularity, the familiar laws of the universe no longer apply, launching scientists into a world of uncertainty and theoretical speculation. The complexity of dark openings and their inherent variability pose significant obstacles to our understanding. While they adhere to a common 3-layer structure, each dark opening exhibits unique characteristics and behaviors, defying simple categorization. As such, Traditional methods of scientific inquiry prove insufficient for studying these cosmic behemoths, which require innovative approaches to unravel their mysteries. Indirect observation remains the primary means of studying dark openings, as direct investigation is rendered unfeasible by the immense gravitational barriers. Attempts to insert probes into dark openings would undoubtedly lead to their destruction, crushed into obscurity by the unstoppable forces at work. Nevertheless, researchers persist in their quest to decipher the secrets of these cosmic giants. Various theories, ranging from cosmic dynamics to stellar collapse, offer tantalizing glimpses into their origins and behavior. Notably, NASA's investigation of M87's cosmic center revealed compelling evidence of a supermassive dark opening exerting its gravitational influence over vast cosmic scales. Despite these mysteries, the pursuit of knowledge continues, driven by humanity's inherent curiosity and desire to comprehend the universe. While dark openings may remain an unsolvable mystery, the unwavering commitment of scientific investigation promises to illuminate the most obscure areas of the universe, revealing its deep secrets. The groundbreaking work of Roy Kerr in 1963 presented a paradigm-shifting perspective on dark openings. He proposed a revolutionary theory of black holes that never stop spinning. Central to Kerr's model was the concept of the ergosphere, a region surrounding the dark opening where divergent forces balance gravitational collapse, preventing further inward destruction. This novel domain displayed curious deviations from traditional physics, hinting at the deep mysteries buried in the shadows of these openings. However, the most intriguing implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This hypothetical structure offers the possibility of a space-time gateway, providing a conduit between distant regions of the universe, or even parallel universes. Wormholes originated from the intricate interplay between Einstein's theory of general relativity and our understanding of reality. In this framework, existence is woven into a four-dimensional fabric. Massive objects warp this space-time fabric, creating gravitational fields that influence the motion of surrounding matter, wormholes. This relentless pursuit of understanding, driven by curiosity and fueled by the spirit of exploration, continues to push the boundaries of theoretical physics and cosmology. Wormholes, though still confined to the realm of hypothesis, inspire both scientific inquiry and the imagination of storytellers, bridging the gap between the abstract and the tangible. Beyond wormholes, dark openings continue to present questions that challenge the very core of modern physics. One of the most significant areas of investigation concerns the reconciliation of general relativity with quantum mechanics. While general relativity governs the behavior of massive celestial bodies and the curvature of spacetime, quantum mechanics describes the behavior of the smallest particles in the universe. These two pillars of physics, however, clash at the singularity, where space and time break down and the known laws of nature cease to function. This paradox has led to the development of new theories, including quantum gravity and string theory, which aim to provide a unified framework for understanding the universe. Hawking radiation, a theoretical prediction by Stephen Hawking, further complicates the picture by suggesting that dark openings are not entirely black. They emit faint radiation due to quantum effects near the event horizon. Over unimaginable time spans, this radiation could cause the dark opening to lose mass and eventually evaporate entirely, leading to profound implications about the conservation of information in the universe. The idea that information might be lost within a dark opening, a concept known as the information paradox, remains one of the most hotly debated topics in physics. If true, it would violate a fundamental principle of quantum mechanics. If not, then some unknown mechanism must be at work to preserve or return that information, even after the dark opening has evaporated. Resolving this paradox could unlock a deeper understanding of the universe's most foundational laws. On a more observational front, technological advancements continue to enhance our ability to study these elusive entities. Space-based observatories, such as the Event Horizon Telescope, EHT, X-ray telescopes like Chandra, and gravitational wave detectors such as LIGO and Virgo, are opening unprecedented windows into the cosmos. These instruments allow scientists to observe the collisions of massive dark openings, detect the ripples in spacetime they produce, and capture real-time data from cosmic events once thought inaccessible. Such observations are not merely academic. They carry the potential to answer some of the universe's greatest questions. How do galaxies form and evolve? What is the ultimate fate of matter drawn into a dark opening? Could wormholes ever be stabilized for travel? Are there forms of matter and energy that remain hidden from us, locked away within the gravitational grasp of a black hole? As we stand on the threshold of deeper understanding, the mysteries of dark openings and the exotic phenomena they encompass remain both a challenge and an inspiration. In confronting the unknown, humanity is not just seeking answers, it is participating in a grand tradition of exploration that stretches back to our earliest stargazers. From ancient myths to modern science, the cosmos has always been a mirror reflecting our greatest hopes, fears, and ambitions. Dark openings, with their immense gravity and infinite mystery, are no longer just distant points in the sky. They are symbols of the frontier, of what we know, what we dream, and what we are yet to discover. The enticing prospect of cosmic portals and alternate realities invites humanity to consider the enigmas of the cosmos and contemplate the infinite possibilities beyond. The quest itself, for a unified theory that reconciles gravity, regions that appear to be spread out, and the rise of quantum mechanics, has looked for a theory that covers everything, a comprehensive system that can incorporate all fundamental forces and the universe's particles. At the forefront of this endeavor stands Michio Kaku, a well-known theoretical physicist whose groundbreaking work has propelled the investigation of superstring theory. The theory of strings is a dramatic departure from conventional ideal models, hypothesizing that fundamental particles are not point-like entities but rather microscopic vibrating strings. These strings, much like the strings of a musical instrument, reverberate at particular frequencies that lead to the different forces and particles found in nature. In this paradigm, the universe becomes akin to a grand symphony, with each particle corresponding to a unique harmonic resonance of these fundamental strings. One of the most striking implications of superstring theory lies in its potential to explain enigmatic phenomena associated with dark matter, wormholes, and other exotic solutions to Einstein's equations of gravity. As strings traverse the fabric of spacetime, their dynamic motion leads to the formation of gravitational singularities and topological anomalies. Despite this, the elegance of superstring theory masks its inherent complexity, as it necessitates the existence of additional dimensions beyond the familiar 3 spatial dimensions and 1 temporal dimension. These extra dimensions, hidden from direct observation, pose a significant challenge to human intuition. Models such as the fish analogy, in which a fish inhabiting a 2-dimensional lake cannot perceive the 3-dimensional world above, provide a glimpse into the mysterious nature of these more advanced dimensional realms. The compactification of these extra dimensions, akin to the folding of a rolled-up piece of paper, renders them imperceptible at everyday scales. Yet, their influence is felt right down to the material fabric of reality. The exact nature of these hidden dimensions remains elusive. A promising explanation is their presence being responsible for the oddities and complex structures observed in the universe. Furthermore, the mathematical underpinnings of superstring theory have brought about a renaissance in mathematical physics, revealing profound relationships among dynamic mathematical patterns and physical phenomena. The pursuit of a theory of everything has catalyzed the union of disciplines, shedding light on the deep interplay between the natural and mathematical sciences. Despite its superior beauty and scientific potential, string theory remains an untested framework awaiting experimental validation. The elusiveness of additional dimensions constitutes a formidable obstacle to experimental verification, relegating superstring theory to the realm of mathematical speculation. Nevertheless, the audacious vision of superstring theory continues to captivate the minds of enthusiasts and researchers alike, enticing the human race to embark on a journey of intellectual discovery and exploration. As we venture deeper into the unexplored areas of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the vast mysteries of the universe, poised on the threshold of a new era of understanding and enlightenment. The task of unraveling the secrets of quantum dark openings has long perplexed physicists, representing a significant threat to our comprehension of the fundamental nature of the universe. Despite numerous efforts by physicists to solve this mystery, an elusive solution has remained beyond our grasp. This prompted Edward Witten of the Institute for Advanced Study at Princeton to describe superstring theory as 21st-century physics that accidentally entered the 20th century. However, recent advancements have incorporated new hope into the search for comprehending dark quantum openings. Several groups of physicists have independently reported a significant breakthrough, uncovering that string theory could provide a complete solution to the problem, albeit within the more restricted setting of 2 dimensions rather than the full 10-dimensional framework set forth by conventional superstring theory. While this represents a promising step forward, the quest for a complete resolution continues to grapple with the complexities of the situation, presenting substantial hindrances. The search for a single theory of everything calls us to investigate the deepest recesses of cosmic existence, where the boundaries between reality and theory become hazy, and the secrets of the universe await discovery. The study of dark spaces carries significant implications for our understanding of the universe, testing our ideas of reality and raising questions about the nature of existence itself. The interplay between dark openings and other astronomical events, such as neutron stars and gamma bursts, reveals the intricate processes at work in the cosmos. The exploration of dark openings and their interaction with surrounding matter continues to reveal a wealth of intriguing phenomena. One of the most fascinating aspects of these cosmic giants is their ability to warp spacetime with such intensity that they produce gravitational waves, ripples in the fabric of spacetime itself. These waves travel outward from their origin, carrying information about the dynamics of events such as the collision or merger of two black holes, or a black hole with a neutron or stellar mass star. Detection has evolved into a powerful tool for studying the universe, particularly since the first direct observation of gravitational waves through the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. This opened a new avenue for research, an astrophysical window that allows scientists to observe the most violent and energetic events in the cosmos with unprecedented clarity. As these observations continue to accumulate, they bring us closer to understanding the true nature of dark openings, their formation, and their evolution. One particularly puzzling aspect is how matter behaves as it falls into a black hole. While current models suggest that matter undergoes extreme transformation as it approaches the singularity, questions remain about the fate of the information contained within that matter. This is known as the information paradox, a problem that has baffled physicists for decades. According to quantum mechanics, information about a particle state cannot be lost. Yet, black holes seem to erase all information that falls into them, challenging the foundations of quantum theory. Resolving this paradox remains one of the key objectives in modern theoretical physics. Furthermore, the possibility of a connection between dark openings and the overall structure of the universe continues to be an active area of investigation. Some hypotheses propose that supermassive black holes at the centers of galaxies play a critical role in shaping individual galaxies, affecting their development and even driving the formation of stars and planetary systems. The relationship between dark matter, dark energy, and these cosmic giants is also the subject of close scrutiny. Understanding how dark openings interact with these enigmatic parts of the cosmos may be necessary to unlock many of the universe's greatest